All right, so we're going to go ahead and get started. This is identifying slow queries and fixing them for obviously, well, hopefully obviously, Postgres Open 2011 here in Chicago. All right. So who am I? I'm Stephen Frost. I'm a systems architect, designer, DBA, Unix admin, what have you. I've worked on Postgres and PostGIS for quite a while. With 8.1, I added roles, and then I did column level privileges in 8.4. Which is certainly something that I think a lot of people like. Kind of the plug, my company is Noblest. We do a lot of government consulting work, so if you're into that, let me know. All right, so the idea here is that we want to find the slow ones first, okay? So this is about trying to figure out what queries in your system are slow, which ones are performing poorly, and what we can do to fix them. So first of all, you have to monitor your systems if you're going to figure that out. So you always want to make sure that you're looking at what the log files have in them. Never start with the default log configuration from Postgres. It sucks. You probably want to turn on logging of checkpoints. You want to log connections. You really should be logging all of your DDL. I mean, that's something that I would certainly encourage. And you might be able to log your DML too if you can get away with it. So DDL are your create table and create index statements. Your DML are your updates and inserts, which can get kind of painful if you want to log all of them. There's lots of different options out there. You've got Nagios with Check Postgres. We'll talk about that. You can do performance measuring as well. You can pull out lots of really interesting information out of PG Bouncer statistics if you're using them. PGFuin is an excellent tool for doing log file analysis. It's got some requirements about what your log line prefix looks like, but that's not really a big deal because you ought to be looking. They should look like that anyway. So they've got a really good default for really good. It's not a default configuration, but a really good configuration for what it should look like. Check Postgres is something that you would use with Nagios. There's tons of useful checks, including ones that can help you identify performance issues, like looking for bloat, looking for idle connections or idle in-transaction connections, which might be holding locks, which can be a huge problem. I'd also tell you about number of log files, and then you can integrate it with your favorite RRD tool-based systems, such as Munin or Cacti or MRTG. You can pull out information from, how many connections there were, things like that, over time. So, finding slow queries. Postgres gives us a lot of really useful options for how to find the slow queries. The best one, at least from my perspective, is log min duration statement. You can change this. All it needs is a reload. What this does is it'll actually log statements that have taken a minimum duration of, X milliseconds. So if it takes 500 milliseconds, you can have it log every query that took that long. And that it'll log DDL, DML, whatever took that long. Lots of other options I talked about a little bit already. Log line prefix. The default one doesn't tell you much of anything. You want to put in lots of information in there, like what host is being connected from, what user is being logged, timestamps. These are all really valuable things to log. And so one of the really key things in identifying slow queries is making sure that you can find them. And you find them by turning on lots of logging options. Logging lock waits is also really useful. This will tell PG to log any time that it has to wait to acquire a lock over, I think it's 10 seconds or something. So if it takes that long to acquire a lock in your system, something's wrong. So that's something that you really should be doing as well. Log statement, again, we'll talk about that a little bit later, but it's basically identifying which kinds of statements get logged. And this is just a real short example of what a PG log might look like. So it'll have a log statement. If you've turned on a lot of things in logline prefix, you'll see additional information in there. But the point here really is that it shows you the duration of the statement, how long it took to execute, and then what the statement was that was actually executing. It's a little bit different from what you might see with PSQL's timing option, if you've ever used that, which can be pretty useful as well. The big difference with PSQL's timing option is that the timing actually in PSQL is how long it took to get all the data back to the client and actually finish that command all the way back to the client side, whereas the duration statement that you'll see on the server-side logs, or if you do an explain analyze, is basically what the server-side piece took. So those can be a difference. And it's important to realize that difference because it could be due to network latency or other things that are causing that problem or causing it to be different. More stuff. So there's a little bit of hokey pokey with the different log min duration statement versus log statement and the different configuration options. If you have log min duration statement, just that turned on, you'll get the duration and the actual statement. If you have log statement all and log min duration statement, what you'll end up with are two different lines, which is really obnoxious. So that's just something, it's just kind of a gotcha when you're configuring things, because the Postgres folks figure, well, you don't want to see the statement twice, essentially. So what you'll get is you'll get a log statement for everything, and then you'll get a timing statement for every time a particular query took longer than your log min duration statement value. If you've got no statement logging turned on, but you also have min duration statement and log duration. So log duration actually basically logs the duration of every query, not just those that took over a certain amount of time. So again, you'll get this weird double line stuff, and so you'll get a duration statement for queries that you don't actually see in your log. So it's just something to watch out for. You want to just be a little bit careful for how you're doing it. What I would recommend typically, if you can afford it, is log statements all along with log duration. But that often isn't cheap, basically because you're logging every insert, you're logging every select, every update, everything. And that ends up being really expensive on a big production host. If you can afford it, great. If you can't, then log min duration statement's your next best bet. That way you're just logging things that are taking an inordinate amount of time. And that varies depending on what you're doing, but if you care about it that much and you care about making your queries fast because you're running a web host or something, my suggestion would probably be 50 milliseconds. If it takes longer than that, you ought to look at it, figure out why it's taking that long, because those add up really, really quickly. And that's kind of what this bottom note's all about, is even if it's going really fast and everything's only taking 20 milliseconds, if you have 32,000 of them, it's going to suck. And that can happen on some page loads. There can be a ridiculous number of queries back to the back end. All right, so once we've identified what queries are slow, we've got to figure out why they're slow. Right, so there's some easy options for this. Maybe you didn't do any kind of configuration. You left the defaults alone on your Postgres configurations. There's dead tuples and bloat that you can have. Those are usually pretty easy to correct, although there's some specific ways you want to do that. And then you want to look at kind of the next level, is how did you write that query? What did the plan end up looking like? How many here are familiar with Postgres plans at all? Do you know what Postgres plans are? All right. That's good. That's good, actually. I like to see a lot of people who aren't in here, just ringers in here trying to trip me up. All right, poor PG configurations. In other words, you use the defaults. The defaults are horrible. They just are. Never stick with the defaults on a PG box. You want to, first of all, look at these particular ones. I would recommend workmem is a really, really important guck, which is basically a configuration option in Postgres. It's called a guck. Workmem says how much memory can it use for a hash table, a sort, how much memory can it use during joins, all that kind of information. All those different types of tasks are what ends up going from workmem. Maintenance workmem is about creating indexes. Effective cache size is how big do you think how much of the memory in the system do you think will be used for caching disk I/O, or disk information, right? So the kernel is going to cache as much as it possibly can, but if you've got a box where you've got 8 gigs on the box and you've got Postgres configured to use 2 gigs of it, then at most you're going to get 6 gigs used for disk cache. So that's where you would want to configure effective cache size to like 6 gigs. It doesn't seem like it's important, but it's actually really, really valuable, because Postgres uses that to figure out what kind of plan to execute once it gets down to figuring out how to plan a given query. Shared buffers is also really important. This is kind of Postgres' own internal cache. So you've got the disk cache, or the OS level disk cache, and then you've got the Postgres cache or shared buffers. So this is something you really need to configure, because the default is 24 megabytes. Unless your database is only 24 megabytes, you really want to increase this value to something reasonable. And something reasonable would be a gig or 2 on an 8 gig box. Checkpoint segments. This is another really important thing. The way Postgres writes out write-ahead logs is using checkpoint segments. And so every time if you only have a certain number of checkpoint segments, then after writing out that many checkpoint segments, each one of which is, or each segment, each one of which is 16 megabytes, it's going to do a checkpoint. When it does that checkpoint, it kills everything. I mean, basically, you'll see checkpoint spikes that are horrible and end up taking a heck of a lot of time to complete. And during that time, it's just busily killing the drive by writing as much as it possibly can. So having more checkpoint segments is good. The default's like 3. I run boxes with like 20. It's something that you really want to make sure that you identify and realize that it's a big difference. Another big thing is to watch out for differences between your production and your development environments when you have PG configurations, because the developers might have it configured, you know, maybe they said, well, workmem's 100 gigs. So everything's fine and hunky-dory when they run this thing on their development box, and it uses a gig to do that hash table. Well, if you can't afford to do that, or you can't afford to do that because you can't set your default work mem up that high on your production boxes because you've got 50,000 different people connecting to it, you got to realize that there's a difference there and make sure that you account for it, and maybe you do it just for that one query or something like that if you really need it, or you come up with a different way to rewrite that query. There may also be differences that are kind of not obvious or unseen. So one of these big ones is statistics. All right? Statistics are basically Postgres, as it's running, collects statistics on every action that happens. And on every table, it gathers statistics using vacuum and analyze, really, vacuum analyze. But those statistics can change plans. If Postgres thinks the table is only 2 rows, it's going to have a different plan than if it thinks it's 20,000 rows. All right? And so if you get those kinds of differences happening between production and development, you're going to have things running in development that might run really fast because it thought there were only 10 rows when there was really 20,000 rows. So that's one of the things and one of the risks a little bit of when you're doing any kind of performance analysis in development. If your development boxes or your staging boxes don't match exactly to your production systems, you can run into these kinds of problems. And even if they do, you know, the frequency of updates, it still gets hairy. So you've got to be careful of it, and you want to watch for plan changes, but we'll get to that in a minute. Obviously, there's differences in hardware, and you got warm-up time and whatnot. All right, dead tuples and bloat. Who here knows what a dead tuple is in Postgres? All right, yay, Robert's here. All right, so a dead tuple in Postgres lingo is a tuple inside of the heap, right? The heap is where Postgres stores all of its data, right, in the files on the file system, okay? It uses multi-version concurrency control. And the way that and so what happens is that when a row becomes not visible to anybody else, it'll just mark it and say, that row's dead. Okay, we can use it again, which is a good thing. You want to be able to use those rows again because you don't want to constantly be expanding the size of the files on the file system. That's actually worse. But if you load a table and you load 1 million records into a table, and then you issue a delete query, it goes through and it marks all of those rows as deleted. And then you insert another 1 million rows. Well, unless you've waited long enough or you've done a commit and waited for the vacuum to come mark all those rows as available for reuse, Postgres will take another 1 million rows off the file system. Right? It'll have basically 2 million in terms of the size of the file on disk, 2 million, room for 2 million tuples instead of only 1 million, which is what's actually in the table. That means that any sequential scan going across it takes twice as long because it's got to read through that entire table in order to do a sequential scan. So one of the things you have to watch out for is bloat, and one of the things that Check Postgres is really good at is identifying where you have bloat. And you can figure out if that's a problem for you. I would say more than about 20% on like an online transaction processing system is probably getting to the point where it's too much. You might want to consider doing something about that. On a data warehousing type of system, it's not as big a deal. Again, some bloat is good. You want to have some room in your table for new tuples to go into, but you don't want too much, or it ends up making other things slower. The way that you can get rid of bloat, the way that I think most Postgres folks would recommend getting rid of it, is using cluster. Cluster will take out an exclusive lock on the table, which, yeah, that sucks if it's a production box, but it'll basically open up a new file, read all of the live tuples, and write them into the new file in order. And in fact, it'll actually cluster it around an index if you've got one on that table, like a primary key, which will speed up future queries against that table if it's using the primary key, which is typically how you want to do things. But One of the downsides of clusters, of course, it takes a lock. There's some workarounds for that online. PG reorg is a pretty good one, which will do the same thing, but allows it to be more or less online. We don't have anything in core yet that does it, but hopefully we will eventually. All right, now for the fun, database magic. Sadly, there is no real magic. Okay, there's only a few different ways that data can be gotten off the disk. Okay, the options are sequentially step through every record in the table and figure out which ones you actually want to keep. All right, that's known as a sequential scan node, which is very fast if you actually need the entire table. But if you don't need all of the table, then you want to go just pull out those individual records or pages that you actually need. That's where you have an index. All right, so for picking out specific records, you use an index. That's going to be known as an index scan node. All right, this doesn't work for a lot of data coming out of that table, and it's amazing how close to the how small an amount makes a difference. For example, I've typically used the rule of thumb of about 5%. If you're going to pull out more than 5% of a table, it's faster to read the entire thing than use an index. The reason is because indexes do random I/O. They access parts of the file system all over the place, and that means the disk head's spinning all around, and you're not using the read-ahead cache that's available in the kernel at all, and it ends up making it slower. What's nice is that it can return the data in order. So if you've got an order by or a sort or something that has to be done on the data, that can be faster if you're using an index scan. Of course, the index has to actually be there to get that to happen. But this is pretty much it. This is how data comes off the disk. So there's not a lot of magic here, and you have to work with what you've got. All right, so who here knows what a join is? All right, there we go. Okay, good. So that's an important piece here, right? I mean, if you're not doing any joins, then the first slide is fine. All right, we're done. All right. So when you want to do a join, there's only a couple different ways. There's a bit more than there were for how to pull data off the disk, but the way you do joins are you can have a nested loop, right, which basically is how most application developers implement joins. And they don't care how big it is. They just they have one loop, and then they have another loop, and they go through and figure out where they match, right? It's like the most inefficient way in the world to do a large-scale join. So that's fine for small data sets, but don't do it for large ones, and never let your application programmers write a join. Joins should be done in the database. It's much, much, much more efficient. All right, another way to do it is with a merge join. This is where you take two ordered sets. You presume you've already sorted the data coming off the file system in some way using a sort or an index scan. And then you merge them. You say, okay, I'm going to take all the ones from this side until I get to one that's past this guy over here. And then I'm going to swap, and then I'm going to put him in and keep going on the other side, right? It's like a deck of cards, right, where you're just kind of interlacing, interleaving everything together. It does require sorted inputs, but can be really good for large data sets and really works if you have indexes on the two things that you want to do this merge join on, because it'll do an in-order index traversal on each one, and it'll just interleave them, and it's great. Probably not what you want for small data sets or for production things because of the requirements that it be sorted, and because a lot of times that's things that you want to do with a smaller data set, and it's going to be faster using a hash table, which is the next one. Right, so the last one here is probably the one you want to see the most. It's a hash join. Hash joins basically, I say they require lots of memory. It's really not that bad, right? If you've got a 100-row table and you're joining that against a 3 million row table, the idea here is that you take the 100-row table, you hash it, and then you step through the 100 million row table or 3 million row table, right? And every time you get something over here, you look it up in the hash table, right? Lookups in a hash table or an order one operation really fast. So it does take a little while because it has to build that hash first. It has to build the actual hash table. That means it has to scan the relation that it's going to build the hash table on top of. And then, then it can actually start operating. So it can be slow to start, but typically that's what you probably are going to want to do, especially if it's a small table against a big table or a small data set in general. Aggregates. Aggregates are something you have to be really careful about because there's almost no way to get away from the fact that if you're doing a summation across all of the rows of the table, you have to visit all of the rows of the table. And you have to pull out that data from every single row, which is very expensive. Same kind of thing with like a count star. Very expensive to do because it has to look at every record in the database or in that particular table. So you want to be careful of that. There's some options for how to deal with that. Actually, I can talk about it a little bit later. All right, so what's the best plan? How do we put all these different nodes together and make sense out of it? So it depends, right? And the entire Postgres optimizer is built around trying to figure out what the best plan is. The way the database figures this out is that it gathers statistics using this analyze function. Now, thankfully, probably all of you are on recent versions of Postgres where you have auto vacuum and it's automatically going through and doing your analyzes and handling and gathering all that statistics for you. So that's wonderful. But if the stats are wrong, or you turned off auto vacuum because you thought it would improve performance, or something else, or it was causing you load or something, you're going to find out real quick that if you don't have current statistics, your plans start to really suck, right? I mean, it gets horrible, right? So here's a really, really kind of stupid, simple example of a case where, all right, the explain analyze I ran against this index scan said that I'm going to get 9,000 rows, and I actually got 163,000 rows back. Well, chances are, if that was a large portion of the table, would have been faster to do a sequential scan instead of an index scan. And it's just a very simple, straightforward example of a case where it can perform really badly if you pick the wrong one, and that's based a huge amount off of what the statistics are. Now, there is a tuning parameter called a statistics target. Okay? What this basically does is it tells analyze and auto vacuum how many different pages, what portion of the table to visit to gather these statistics. It doesn't read the entire table. Okay, reading the entire table would take forever. I mean, if you're going to do that, you might as well just do that and be done. So what it does is when you run auto vacuum is that it visits a portion of the table. Or when you run analyze, it visits a portion of the table and gathers statistics based off of that information. So you might want to increase that if you're getting bad plans, ones where the numbers don't look terrible, but they're not as accurate as they could be, and that's causing some changes in what your plans are. So the default actually in the latest version of Postgres is better. I think we upped it to 100 instead of 10, which is certainly much better than what it used to be. So it hopefully is not as much of an issue if you're using a recent version. All right, so now we got to figure out what plan from all this did Postgres end up using, because that's what we're going to try to impact. It doesn't look quite as well as I'd hoped. I'm sorry about that. So the way you do it is you use explain. All right, you take explain and you stick it in front of whatever your SQL statement is. All right, this is a simple select star with a simple join in it, where we're joining a couple of tables that are in the catalog. All right, and this is going to use a hash join, which is good in general. Realize here that it's doing sequential scans because I'm going to take everything out of these two tables and return them. At least everything that matches that join condition, which is, in this case, most of it. So here we have just a quick example of what a hash join looks like and what sequential scan nodes look like. So explain, if you're doing query optimization, you want to get really, really familiar with what explain looks like and how it operates. All right? And it also gives you some idea of what the costs are. These cost numbers are not, they don't match back to milliseconds or any kind of actual time, right? It's just a statistic, essentially. It's just a way for Postgres to decide, do I want this plan or do I want that plan? And it does that based on which one costs the less in this kind of notion of what a cost is. There's some other ways that you can impact that cost. If you've got SSDs or something, you could go change what the random page cost is, because on an SSD, you're going to have less penalty from randomly searching around than you would on a solid-state drive typically, or on a spinning drive typically. All right, adding a where clause. Where clauses are really, really good because it tells the database what do you really want. And it allows the database to filter out information that you don't care about. So in this case, we're adding a where clause of rel name equals PG class. Oh, all of a sudden we don't even have any sequential scan. Well, we have one sequential scan on PG namespace, but it's 6 rows, right? Oh no. That's not so bad. But the point here is that we have an index scan, right? And the index scan is a heck of a lot faster, because it takes that piece of information that you just gave the database and says, oh, I know where to find that. And in fact, I can find that and I can just return that to you. I'm not going to return everything. I'm not going to return the entire table. You don't want it, you don't need it. I'm going to give you just that one thing you're looking for. So in this case, what you see here is there's a nested loop and an index scan and a sequential scan. So the nested loop is a little bit interesting, right? This is one of the ways that you can do a join is using a nested loop. This works in this case because there's very, very few rows. I mean, if you look, the actual output from that nested row is only one row. And this is all just using statistics. This isn't an actual, it didn't run this query. It just said, looking at my statistics, I think this is only going to return one row, and therefore I'm going to use a nested loop to do that. Here is an explain analyze output. This is your other best friend when you're trying to do query optimization. All right? Explain analyze actually runs the query. It actually runs the full query and then essentially rolls it back. Okay? So what it will give you is all of, well, take that back. It will roll it back if you do a rollback. If you commit, it'll actually commit whatever you did. But it actually runs the entire query. So here it actually will show you how much time it took to do that hash join. Right? These are kind of combined times. These are totals. Right? The actual time, those two numbers at the beginning there, the fact that there's two numbers there, the first number is how long did it take for Postgres to start returning data. Right? This matters because when we're doing a limit, for example, we care about how long it takes to start getting that data. Right? And then the other number is the total time in that piece. So what you have here is a hash join, a hash condition, of course, the sequential scan, and then here in more recent versions of Postgres, we've got actual information about how many buckets there were, how many batches we had, and what the memory utilization was. Right? So this is obviously a really simple case where we only used 1 kilobyte of memory, but this can get very important because if Postgres figures out that it's going to need more memory than it thinks you have workmem configured for, so say you've got workmem at whatever the default is, which is 1 meg, I think. Right? So if you have a default of 1 meg with memory usage, and you have a table that's 2 megabytes in size, Postgres won't use a hash on it. It won't even try to generate a hash table for it because it knows that that's going to go above what your max cap on a hash table is. And that ends up being really, really terrible. Again, configure these things, please. Workmem I would put up at, well, I've put it up at really high numbers before, but I think 64 megs is probably pretty reasonable for a pretty busy, decent-sized box. Oh, and the last thing on this one is the fact that those two different total running times at the bottom, I mentioned this earlier, I have PSQL duration on here. So the bottom one is how long it took for all the data to get back to PSQL, right? The top one, the one above it, is how much time it took in the back end to execute. All right, so here's another explain analyze, but this time we're using an index scan with the where. So this shows you how, I mean, if you go back and look, the other one was a couple milliseconds, I think. This one is 0.147 to run this. I mean, it's dramatic how much faster it is. And that speed actually ends up kind of translating into how well your system's going to scale. Right? The faster you can run queries, the more queries you can run in a given time slice. Right? Which means the more your system's going to be able to scale, the more it's going to be able to handle it at a single time. It's still doing a sequential scan on PG namespace, but again, that's a really small table. And so it's actually faster if it's only 1 page of data, to pull in that 1 page of data, than to go to the index and find out it's 1 page and then go get that piece of data. All right, other explain output options. There are a bunch of different options for how to get data out of explain, and you can use a bunch of different tools to analyze it that'll make it a lot prettier than the stuff I'm showing you from PSQL, although that's still my favorite, I have to say. But you can get it as XML, JSON, YAML. You can also, I mean, explain.depez.com is a really, really cool tool. So you might check that out and try taking an explain output and loading it into there. It'll give you nice graphs and nice information on how much time it took, and it'll even highlight the pieces that took like the longest amount of time with different color codes and whatnot. PGFuine, again, I mentioned that earlier, really, really useful tool. I think anybody who's doing anything serious with this kind of performance analysis should be using PGFuine or something along those lines to do it. There are also ways to automatically collect it. Yeah.
When we have tables, partition tables,
Yeah.
and partition is not natural partition, right? So how it's in explain it shows. Whatever I saw, it's kind of really, really not realistic. It shows kind of statistics. And explain for me if you have like 20 partitions.
Mm-hmm. So.
And partition and more than more details with table partitions in different table space.
Mm-hmm. Yeah, the explain is going to end up being pretty huge. And part of the reason for that is because what it's going to do is it's going to tell you kind of all the potential things it could have done. And if things are set up correctly, what you should see on a lot of those is like a one-time filter false. Well, it depends on how you have your partitioning set up. But if you've got like a big view that goes across all of them, then you'll get these one-time filter false things on each node that it's not going to bother traversing. On the other ones, if you're doing actual inheritance type partitioning, I don't think you actually get to see the underlying ones, unfortunately. No, I don't. No, I mean, it will do that exclusion constraint, which is what you're talking about, is constraint exclusion. So you have to make sure you have your check constraints set up correctly. And when you have that done, it'll only actually visit those tables that it identifies as possibly having data for your query. But in terms of getting better details about the explain, from Postgres's position, it's looking at just the parent table. It's that the fact that it goes into the underneath tables is kind of... Right. Yeah, I mean, there are a bunch of child tables associated with it. Well, it is. It's ridiculously small. Right. Yeah. No, I mean, that's one of the things that we need to improve is certainly is how partitioning is handled. Right. I agree with that completely. Right. Yeah, it does have statistics on the individual tables. Mm-hmm. No, I understand. I don't have a solution for you, but I understand your problem. Anyhow, so one of the things that you can do for when you're trying to gather explain information is use this really useful tool called auto-explain. So you can actually set up auto-explain to automatically run and explain on queries that take too long. So when you had log min duration statement, right, that allows you to put into the log file the duration of a given statement and what that statement was. But you don't know what the plan was. You know, you have to like cut and paste out of that and go run that through PSQL with an explain in front of it, and then you can find out what you think the plan was. Of course, the plan might have changed since then, right? It doesn't necessarily mean that that was the plan that was used to execute. So what you can do is you can use this tool called auto-explain. It's not free to run in a production environment. There is some load associated with it, but it's not that bad, really. But this allows you to have an explain automatically run against any query that ran for more than whatever the duration is that you want to set. You can also have it do explain analyze, but that's really, really expensive to do in a production environment because it turns on all kinds of additional statistics collection that's done during the execution of the query, which can get really expensive. No. What happens here is that it'll actually log it if it ran longer than that log min duration. If it didn't take that long to run, if it took less than 50 milliseconds to run, it won't log it, essentially is the answer there. But when you turn on either explain here or explain analyze, it's actually going to do it for every query, right? It doesn't find out until the end how long it took to run. And so it's going to turn on all of this statistics gathering and everything in the executor that's going to end up taking a lot longer to, making that query take a lot longer to run in order to generate that information. So it's not something you really want to do in general against all of your production systems because it's just going to get, if you've got a high load on your production box, adding this is not going to be good for it. Why your result set can't, you mean from coming back from the database in your query?
Rather than effectively
It doesn't actually, here, when you do it with auto-explain, it doesn't actually execute and then roll it back. Right? That was something I mentioned earlier where you might do that in testing. Here it doesn't, but it does turn on a whole bunch of additional things in the executor. Right, right, which is pretty expensive, yeah.
So let's assume I have a very slow query. Let's assume I am the guilty culprit because I wrote it in a way which made this join much longer.
Sure.
So the problem is PostgreSQL has its own query optimizer.
Mm-hmm.
So it tried to optimize.
Yeah.
Now I'm looking at the results of explain.
Yeah.
And trying to second guess or reverse engineer the optimizer and rewrite my query in order to appease it.
Yep.
Okay? That's pretty crooked and it's like rewriting your C program in order to appease GCC, to make it produce better code. Okay?
That happens too, yeah.
Yeah, but it happens, but it is not the right way to approach it. So is there a technique, which would allow me to rewrite my query semi-scientifically, not just by trial and error?
We'll get there.
Okay.
I mean, I've got some specific points towards that as we get through. Right, yeah. We're not going to talk about hints. All right. The other nice thing about auto-explain is that it allows you to get the explain output of what are called nested statements. All right? A nested statement is something that's inside of a function, like a PL/PGSQL function. Right? You can't normally see that very easily by because you can't just run explain on it. If you run explain on a function call, all you get back is the function call. You don't actually get to see any information about how long it took inside of it. There's some hokey pokey you can do to try to get what the actual plan would be for that, but it's a lot easier just to turn this on and then run it. And then you'll see, because it'll actually log the nested statements from what was run by PL/PGSQL and give you what the explain results of that would be, or were actually when it ran it. All right, how to change the plans, how to fix the queries. All right, fixing them. So there's lots of low-hanging fruit that these catch actually a lot of things, which is kind of insane. If you've got a query that's only returning one record, even though you're using a sequential scan, you probably forgot an index, right? I mean, this is pretty basic stuff, but for developers, they might not realize or understand this. If you're using a merge join for a small data set, make sure that your work mem is big enough that it could have considered something else, right? Perhaps a hash join would be most likely what you'd want. If you're getting a nested loop with a large data set, it's probably because of a bad row estimate, right? And so what you want to do from that case is run your explain analyze, see how many rows it thought it was going to get back from that, and see what the actual was, right? In that case, you want to make sure that you're getting analyzes done, right, across those tables, make sure auto vacuum is running, all that fun stuff, and you might want to increase the statistics target. So that tells Postgres to look at more records in that table to figure out what the good statistics are, which ones are really the most common values, that kind of stuff. If you have deletes that are slow, you want to make sure you have indexes on your foreign keys, right? Postgres does not require this, okay? So if you're running a delete on a table that's referenced by another table, and you have it set up to do cascading, so that when you delete it off this, it'll delete it off the other one, then if you don't have an index on that other table, it's going to sequentially scan it to find the records to delete. Sucks. You don't want that. That's terrible. So you want to make sure you have indexes over there as well, just to make sure that it's fast. Yeah?
Isn't cascading allowed in PostgreSQL only on primary, foreign key constraint, isn't it allowed only on primary key?
No.
Any unique?
Yeah. Should be any unique. You can have it on more than just primary keys. All right, so harder items are looking over longer running queries. That often gets to be kind of obnoxious, but if you actually are logging things correctly, you can see those pretty quickly. Again, when you're using stored procedures and triggers, that can help, that can hurt, depends on what you're doing. Another solution is, of course, partitioning, like we were talking about before, where you actually take your data and you break it up into multiple different tables. And then you can have a parent table over top of those that you can query to check out all those, they'll return all the data from all those tables. And then you set up your where clause correctly, and it'll only look at those tables that are going to satisfy the constraint that you have on the where clause. You can also look at partial indexes and functional indexes. These can be really, really useful. A good example of this is that if you've got a column in your database that is 90% of the time null, right, and only 10% of the time actually has useful data in it, well, what's the point of indexing all of those nulls? There's no point to it, right? So you can actually create an index that only indexes the 10% that matters, right? But when you do that, you have to make sure that when you query against that table, you have a constraint in your where clause that says you don't want nulls. So otherwise, it won't use the index. You can do the same kind of thing with functions. All right, so these are just some examples of these cases. So this is an example of a sequential scan, right, which only returns one record, but does a sequential scan, right, even though there's 20,000 rows. And now this is a huge difference when there's an index on it, right? So now you've got an index on it, and the runtime goes from 50 milliseconds to 0.09, right? And then you can do an explain analyze. Now here's an interesting one, right? If you're using a like statement, right, or an I like, or any kind of text operation along those lines, even regular expressions, you're going to end up not getting the index utilization that you would otherwise hope for. Well, there's actually a solution for that. And that's called create a text pattern ops index. So if you actually create a special kind of index on that text column, right, using the text pattern operators, now all of a sudden your scans will actually use that index, all right, which is hugely beneficial when you are using text columns. Now, you do have to keep it kind of simple in this case, right? The pattern has to be anchored. That means it has to either start at the beginning or you can have it start at the end. But if you do it at the end, you have to reverse what the text pattern is actually, what the index is indexed on. You can have an index reverse if you happen to be searching for what's at the end of a string all the time. But it's extremely useful to use this. Again, you can also do this for regular expressions, but it has to be anchored. So if you put a caret at the beginning of your regular expression, it'll use this, all right? As long as the regex is simple enough. How many people here are familiar with regexes? All right, so a fair number. So if you have a case where you've got an open parenthesis, right, you can have a caret. As soon as you put an open parenthesis there so that you can have multiple different options for the regex for what could be at the beginning, boom, that's it. Forget it. Postgres isn't going to try. It's too complicated. All right, the text pattern operator stuff for regular expressions it's got to be simple. Better way to do that, use ORs. And then Postgres will figure out if it can do a nested loop instead, and that'll be faster. Or you could do like an in any, but you have to repeat the regex for every permutation that you care about. So we also have really, really good full text search and indexing. It's actually really good, and there's even different types of indexes that you can use. You can use gist or you can use gin. And they have some different trade-offs for when one might be better than the other. So, but that's for full text. It's not for substring searching. But it can be really, really helpful. All right. Example of a merge join for small data sets. Right? So here's a case where it's decided to use a merge join, even though, at least according to my book, that's a pretty small amount of data. We're only talking about 12,000 rows. Right? That's not great. Instead, what you can do is if you increase your work mem, then it can use a hash join. And in fact, it gets even better if you use like a where clause or something like that, so you can avoid these sequential scans. But that's something else to watch out for is merge joins. Especially watch out for merge joins on node plans that are underneath it sorts when there's lots of data, right? If you're doing a sort on a huge table to do an aggregate, and you're doing a merge join against another reasonably large table, and it sorts both of those, and then aggregates them, well, if the aggregated result would have been small, that's a horrible way to do it, right? Instead, what you want to do is have a hash table, right, where you're only storing the results of the aggregate in the hash. But Postgres has to know that it can build a big enough hash table in memory without running the box out of memory or violating your work mem constraint, right, on how much memory it can use. So that's one of the big cases I've come across where you really want to make sure that your work mem is set to something reasonable. And for specific queries where that happens, up it. I mean, you can set work mem inside of a given transaction or inside of a given connection to the database. So you don't have to change your default. You can just set it for that one query that's going to run that needs to have it set to something enormous, like 10 gigs, so that it can build that hash table instead of sorting these two 300 gig tables. All right, here's an example of where turning off nested loops is actually pretty, disastrous in some cases. Right? The first query here is 0.112 milliseconds because it used a nested loop. You force it to use a hash join, and all of a sudden it's 46 milliseconds. That's horrible, right? That's 400 times, something like that. I mean, it's just ridiculously, slower. So this is one of those cases where don't play with these these enable options unless you know what you're doing, and never put them in as a default. You might do it, again, these are things that you can set, all these enable, underscore, nest loop, merge join, all these different things. You can set them, inside of a given connection or inside of a given transaction for a particular query, right? If you need to do it for that, that might be all right. It's kind of like hints, but not really. So you can do that, but never set it as a default because you can end up taking queries that used to be, sub-millisecond and making them take forever. So this is just something to watch out for. So if somebody's trying to encourage you to set that for your default, trust me, come talk to us on PGSQL performance or something, because there's got to be a better way to solve that problem. All right, here's an example of the delete issue that we were talking about here before. Right, so here's a case where we've got a foreign key, and what you'll see here is that when you do a delete, when you do an explain on a delete or an explain analyze, you'll see that it's running these triggers. Right, the triggers are what are going to the other tables to delete entries that were matching to the foreign key that was in the table you're deleting from. Right, and so you do get at least some information in here about what happened when that trigger ran, how long it took. It's not like there's an explain for that, unfortunately, although you can kind of mimic it by doing an explain delete on the other table using whatever the foreign key column is. But the point here is that there was, I created an index in between these two on this table, and now all of a sudden, instead of taking this, 3 milliseconds for this delete, it takes half a millisecond. Obviously, that becomes a much bigger value when you have a lot more data in the tables. But the point is here, you want to watch out for, make sure you have foreign keys on those columns when you're creating these. Otherwise, the deletes can get really, really painful. Prepared queries. I think they're good things. I think, in general, that we should be using them. There's a couple of use cases that I've come across where it's a problem to use them, but more generally, I think they're good. Right? This is an idea where you plan it once, and then you run it lots and lots of time. And that means that you don't have to replan it every time you execute it. It also means that variables aren't substituted in until it's actually executed, which means that Postgres can sometimes use those values, those specific values that you pass into it, and so the plan might not be quite as good, but it's going to typically be a lot more stable, and so it's not going to change on you because you changed what value you put in that statement. It doesn't let you do, you can't do constraint exclusion with it, which is a problem if you're using a lot of partitioning. And here's an example of something that I get asked a lot, which is how the heck do you do an explain on that then, or an explain analyze? This is it. You actually prepare it using an explicit prepare statement with an actual name, and then you can do an explain on that as if it was a function, but this will actually return and explain, the entire explain tree or the explain analyze tree. So it's not really a function, but it looks kind of like you're calling it. All right, so query review. This is where we'll start to talk about some of the ways that you can kind of try to figure out, okay, what's a way to improve this query or that query, what's going to make Postgres happier. So a couple real basics. Select count star really sucks. Don't do it. If you can avoid it, please don't. Select star from table. This is something that a lot of application developers may do. Well, just give me everything and I'll figure out what I need. That sucks. Chances are you don't really need them all, and you have to realize that you're passing that entire table from the back-end database server to the front-end server, only to have it then be filtered. Order by and limit can actually help, right? I mean, if you only need the top 10 records and you've got an index on that, it'll just go grab the top 10 out of the index, right, on whatever that column is. That's a heck of a lot faster than trying to do it somewhere else. So it actually can be, with an order by and limit, it can be better. So don't be afraid of them, but do run explain when you call them, because sometimes it'll enforce a sort when you don't want it to, or you don't think it needs to. Selecting every column out of a table. This is something a lot of ORMs like to do, even though it gets really expensive. When Postgres stores a wide column, right, a column that's larger than would fit into a regular page, it's going to toast it. That means it's going to create a side table, right? Stick the large value over there, and all it has in the main table is a pointer to it. This keeps your main table nice and small. But if you select star, it's got to go fetch that, right? And that ends up getting expensive if you don't need it. If you're not going to use it, don't query it out. If you only need the ID column, it's an integer column, then it never even has to look at the toast table, right? It can just pull back that one column for you. So that's something that you always want to be watchful of. Never use select star in applications and whatnot. Also, watch out for missing join conditions. This is a fun one. There's no warning here that Postgres will give you saying that there's no join condition for C. So that ends up causing a Cartesian product, which ends up being really, really expensive and giving you lots more stuff. And then your application developer will say, I got lots of duplicates. I'm going to use distinct. Okay, no, don't do that. Right? Because now you're telling it, join all this stuff together, but then only give me the distinct values from it. It's horribly expensive, but that's what they're going to do. So that's another thing to watch out for. I probably should add it to here at some point is if you just see distincts sprinkled all over the place, it's probably because the developer couldn't figure out what the right join clause was. They didn't know what to do to get rid of all the dupes, right? The database isn't going to have dupes in it, typically, right? So that's one thing that you want to watch out for. I would also always encourage using actual, what I would consider more formal join syntax. This will actually complain if you don't put some kind of join condition in, right? If you just say A join B, semicolon, it'll complain. It's like there's no join condition. You got to give me a join condition. So that's one thing where I would always recommend using a formal join clause like that instead of using what I call comma joins, which is the A, comma B, comma C stuff. So that's just another takeaway that you want to probably encourage your developers or encourage your other folks to do. All right, more query fun. All right, select star from X where it's some idea in this huge table. All right, this is not good. Using in clauses in general is not the best idea in the world. It can work, but the results inside of that subquery should be small and should be fast to return. Okay, otherwise it can get ugly. What I would recommend is turn it into a join. Right? Chances are that's what you really wanted anyway. So you can certainly join against it instead of doing a subquery like that, and that's going to end up being something that Postgres can optimize a lot faster. Now realize that you got to think about, okay, is it going to return the same data or not? Right? So these are not all blanket things. You got to make sure that it's actually getting you the data and the information that you want, and the format you want, and whatnot. But more generally, this is the direction I would encourage you to look in to try to solve your query, why this particular query is not working well or whatever. Same thing with a not in. Not in seems like it might be a little bit more difficult, but you can use a left join instead. So you can just select from X and then left join against the big table and say where the big table side is null, right? And that'll do the same kind of thing as a not in. Not exists is actually really cool, and it's something that I find a lot of people are not familiar with. So not exists basically says, check to see if there was any record returned from this subquery. If not, that doesn't count then. And it's correlated, right? So you can actually reference inside of the subquery the value that's on the outside, right? So here I'm referencing x.myid from inside of the subselect, right? So if all you're doing is give me the entries in X where there does not exist an entry for that in big table, then you can write it with a not exist like this. And it's actually, I find it to be pretty efficient typically. But you got to consider the trade-offs and consider how much data is going to be coming back in those subqueries and how many of them are going to have to be done. All right. If you've got a really expensive to generate table that you want to reference multiple times in your query, use a common table expression. This is something that was new in 8.4 or 9.0, one of those. But 9, yeah, 9.0. So if you haven't played with it yet, you probably should start figuring it out even if you're not on 9 yet, because you'll get there eventually, right? So what this allows you to do is, so the first one is select star, but then I also want to know what the summation is, right, across this expensive view that I've got, right? This sucks to do it this way because then you've got two basic queries that are going to run. You've got one that's going to run the entire summation across the old table, right? And then you've got another query that's going to run to actually pull out each record from it. And it's not going to be very efficient. So you can use a with clause instead. Yeah?
Does the corresponding row need the privilege of creating temporary tables for them.
No, no, nope, nope, not at all. This does not actually create a temporary table. It doesn't actually create it. It's just a matter of how you can write the query to make better use of what that data is already in memory. So what this does is basically it pulls out the two queries as actual with common table expressions, and then so you can have more than one common table expression, more than one common table. So here we have my view and my sums. So there's actually two of them here, and then you can actually have a select that goes across them, and you can build on them. So if you want to, you can actually build one with one common table across against based on one that came prior. So you can end up, if you have like a where clause in here, you could actually do a where clause instead. Yeah. What if it doesn't fit in memory? That's it. Well, I think it probably does suck. I mean, in the end of the day. But basically, I think what it would do is it'd find out a way to do it. It would find a plan that could do it on disk. It still wouldn't create an actual temp table, like really, but it would end up doing like a sort on disk or something, which, yeah, could end up sucking. Anyway, so you can also use this to implement recursion if you've got like some kind of tree structure in your database. Yeah?
Does the planner normally find just general common sub-expressions?
Yes, it will do that in some cases. Not, I mean,
Where it's not just sub-expression, it's actually calculated.
yeah, this is actually generating, it's doing more. It's not just like a subset of something, right? It actually has to do, one has to do a summation across the entire thing, right? So there's, I mean, it's really useful to use common table expressions. Admittedly, there are more optimizations for common table expressions that other databases do today that we don't have yet, but it's coming. I mean, it's a relatively new feature. All right, if you need a fast count star, we're actually almost out of time here, so I'm going to go kind of quick here. These slides will be posted up, so if you do need a fast count star or something like it, I would encourage trying to use like rel tuples. This is one of the places where Postgres collects statistics information and puts it. Actually, rel tuples is how many on-disk tuples there are, but basically you can look for having something that's just an estimate. It's not an actual. You can also use a trigger if you need to have it actually be accurate, but you got to watch out for locking issues when you're using a trigger. Here's an example of how you might be able to do a trigger that would just have some side table that keeps track of what the count is in that one table that's really big. Again, these are some different options for the different Postgres gucks. Workmem, these are all things that you've got to configure them. Like I said, workmem, I would put it 64 megs and not even blink an eye at it. Maintenance workmem, I'd set to like a gig. Effective cache size, that should be based on how much you have, how much memory you have, but half of the memory in the box is not unreasonable. Shared buffers, on a decent server should be at least 1 to 2 gigs. You can maybe get it all the way up to 8 gigs on like a 32 gig box or something. Going beyond that, there's some contention about whether it makes sense to go beyond that or not. There's also partial indexes. I think I covered a lot of this. You can tune the background writer, which can be really helpful. And then, of course, there's always buy more hardware. Lots of memory is good. SSDs are really fast. Questions? Yeah.
Can it be downloaded from somewhere?
Yeah. I'll get the slides up. It's not up yet. Yeah.
Have you ever, this is really more of a system tuning thing. Have you ever just used SSD maybe as kind of a secondary cache as a swap device?
I haven't heard people doing that. Typically, they would put their heap on it or put indexes on it. That's pretty common. I mean, you could also put PGA. One of the other big ones is putting. Yeah.
I guess what I'm trying to get at is that, let's say you do have some stuff that would normally be cached. It could be cached in the shared buffer. If they do get swapped out, then effectively,
That doesn't.
let's say
That doesn't. Shared buffer shouldn't get swapped out. I mean, that's shared memory. That should be pretty rare that it gets. Yeah, that'd be pretty rare that would happen. Yes, Aaron.
SSDs, indexes are typically sequentially read, and if you've got a lot of disks in a RAID 10 or something, you can usually tear indexes up off the drive so fast that at the cost of SSD, it may sound crazy for data tables on your SSDs where you are almost always going at them randomly.
We're actually, just so you know, like, we've done a lot of testing with that. The way I'm kind of thinking about this is,
That makes sense to me.
would an SSD as swap be
That I don't think would help. No, that's probably not where I would go with it. All right, unfortunately, all right, last question. Yeah. Yeah. Yep, there's lots of documentations. Look for Robert Haas's talk where he goes in depth about all the explain nodes. All right, if anybody has any other questions for me, feel free to ask me kind of at the back of the room or something, but we need to move along because the next query is coming, the next talk. Yeah, no, I'll get the slides up and I'll tell Selena to pass them out. What's that? The prior slide? Shared buffer.